All right, well, that was fun. Hopefully, you saw that I was in Pamplona because that was running of the bulls. All right, let's get into related rates. Supposed to be related rates. Here we go. 2.6, part 1. Got two parts to related rates because they're pretty awesome. We are going to find a related rate. We're going to write related rates to model real-life problems. Basically, the problem will be there already, and we're going to just write the rate according to what's written. You can read that. I'm not going to really read that. I mean, again, it's a review from last year, so it shouldn't be anything new. Remember, you do have to remember the formulas to all of these shapes, volume, surface area, pretty much everything. You will not be given it for the most part. I mean, you could. It might not work that way, but you could. So the volume of a cone. We should know, hopefully, that the volume of a cone is volume is equal to 1/3 pi r squared h. That's the volume of a cone. Now, I'm going to differentiate this formula with respect to time. Okay, with respect to time. Because in these problems, I'm basically always going to take the derivative with respect to time. Alright, so if I do that, I end up getting dv over dt, or dv dt, is equal to, now this is really 1/3 pi. Okay, that is the constant, right? Pi is technically a constant, so I can shift that to the front. And now I'm going to take the derivative of r squared h. But r squared h is really the product rule, so we got to make sure we know what rule we're using when I do this. And so I'm going to take the derivative, we'll say h is our u or v, or it doesn't really matter. And so this is going to be r squared times 1, because the derivative of h is 1, times your dh over dt. And then I'm going to do a big, what am I going to do? I don't know. I don't know what I want to do. I don't know. Then I'm going to say, okay, well, I'm going to add 1/3 pi in there, because technically this 1/3, I can even put a double parentheses there if I really want to, and then just redistribute that pi thirds through, times, then I take the derivative of the r squared, so that's really just 2r. But because I took the derivative of r with respect to time, I do the power rule like I normally would do, but then I have to multiply by dr dt, and then times that h. So if we clean this up a little bit, I end up with 1 pi r squared dh over 3, and then there's a dt right there. Okay, so, and you could split that if you wanted to, like right here. So just a big multiplication symbol. That's fine too, but that's okay. Then if I multiply this over here, I get 2 pi over 3 times rh times dr over dt. So this is the derivative, and this is dv dt over here. This is the derivative of the formula for volume of a cone with respect to time. Now, most of the time when we actually do these types of problems, we're going to be given values for either radius or height or something. So we won't have all of these dv dt's, dh dt's, or dr dt's. Some of those will cancel because it's a constant, right? Or some of those will be filled in based on what they give us in the problem. So yes, this looks kind of crazy now. It won't look this crazy later when we actually get into some problems. All right, in general, if I'm given a function, was y is equal to x squared plus 3, and we know dx over dt is equal to 2 when s is equal to 1. Find dy dt when x is equal to 1. Okay, so if we're differentiating with respect to time, which is what the last section really was, and called implicit differentiation, where we're taking the derivative of a variable with respect to another variable. So because I'm going with respect to time, each of these are not t, so I have to have some dx dt or dy dt with it. So the derivative of y is dy dt is equal to 2x dx dt, and then plus 0, right? So I don't even have to write that piece. And so dx dt is equal to 2 when x is equal to 1. So that means this 2 is going to go here, this 1 is going to go here. Once I plug those in, I'm able to find dy dt, which is 2 times 1 times 2, which is 4. Okay, so dy dt equals a 4. Now, in some markings or books or whatever, they might say that dy over dt is equal to y prime, or dx dt is equal to x prime. And I might use that notation too, and you have to understand that it's the same thing. Okay? It's the y variable, we're taking the derivative of it with respect to whatever variable we want. In this case it's t. It could be, right, dy dx is the same as y prime. It just depends on what variable we're with respect to. In this case it's x, in this case it's t. Gotta understand that piece. Alright? Alrighty. We're inflating a balloon. So excited. I'm so excited! I'm so excited. It's from a movie, I think. I'm so excited! I forget. It's like maybe Crocodile Hunter? I don't know. Something like that. Okay, so because it says it's a spherical balloon, we want to, what do we want to find? Find the rate of change of the radius when the radius is 2 feet. We know that the volume of a sphere is 4/3 pi r cubed. It's pretty awesome. Alright, now let's take the derivative of that. So I get dv over dt. And because there's only one variable right here, I'm going to basically bring that down. So I get 12 over 3, which is still now 4, pi r squared. Oh, 4 pi r squared, that's cool. That's the surface area of a sphere, right? So what happens when you differentiate the volume or integrate the surface area? You get the next one. Pretty cool. And then times, because I'm with for time, it's going to be dr over dt. Alright, now what else do we know? We know that air is being pumped into at a 4.5 cubic feet per minute. This is the volume, or the change in volume. So because it's the change in volume, that's our dv dt, right? And so I'm going to plug that 4.5 in on the left. I get 4 pi. Well, we know r now is 2. Okay, so I'm going to plug that in. Don't plug the 2 in before you take the derivative. Okay, because otherwise you're not going to have anything. You're just going to get a single number, and you're not going to have anything to really find. Okay, because dv dt we already have. If you plug in r, then we're not actually finding the change in the radius at all. Okay, remember, this stands for change. It's slope. Times dr dt. And so then I can divide, right? It's 4.5 divided by 8 pi, which is equal to dr over dt, which I think is that 8 pi? Oh, it's 2 squared. I can't do math. That's 4, so that's 16 pi. 16 pies. Just like 16 candles. It's a pretty good song, I think, right? 16 candles. 4.5 over 16 pi. If you actually did this on a calculator, you get somewhere around 0.090, and then feet per minute. Because the feet is the radius, alright, and then per minute that's the unit of measure. So this is equal to dr over dt. Great news. Let's move on. Ripples in a pond. A pebble is dropped into a calm pond, causing ripples in the form of concentric circles. Concentric circles, or if you don't know, are circles within 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 bigger circles and bigger circles. I don't know, but that's pretty cool. Okay, the radius r of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area A of the disturbed water changing? So we're talking about area of a circle, so we got to know that area of a circle is equal to pi r squared. Then, again, I have the formula down. Now we got to derivatate it. So I get dA over dt with respect to time is equal to 2 pi r. Whoa, that's the circumference of a circle. Whoa! And times dr dt. Great. Okay, when the radius is 4 feet, so now that's the radius. I'm going to plug that in there. The radius r of the outer ripple is increasing at a constant rate of 1 foot per second. So that's dr over dt. I'm trying to find dA over dt. Okay, so I get dA over dt is equal to 2 pi. R is 4. We just plug that in. And dr dt is 1. So that's equal to 8 pi. 8 pi. And because it's area, we're at feet squared per second. Okay? Feet squared per second. Fantastic. Last one on this one, and then we're going to move on. Where will I visit next? I don't know. Falling ladder. A 50-foot ladder is leaning up against the side of a building. So here's a building. Here is a ladder. And this is 50 foot. Boom. The base of the ladder is pulled away from the wall. The base of the ladder is pulled away. So this is really going this direction. Okay, at a rate of 3 feet per second. 3 feet per second. How fast is the top of the ladder falling when the base, boom, this is falling, question, when the base is 30 feet from the wall. I want to be 30 feet there. What is the acceleration of the top of the ladder at the same point? Pretty cool. So, what do I need? I need some Pythagorean theorem. I know that b squared, or we'll just do a squared plus b squared is equal to c squared. And because this is a right angle, I can do that. I know that I'm going to now differentiate all of these values, right? So there's my formula that I'm working with. Now I'm going to derivative them all. I get 2a dA over dt plus 2b dB over dt equals 2c dc over dt. Great. Okay? This looks like data. DAD. Oh no, that's a 2. Tuata? Then what do? Well, now I can start plugging in some values. Okay. Well, we know that the hypotenuse is 50. And because this is a constant, like this is, the ladder is 50 foot no matter what. If it's like this, or 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 like this, I can't go any further than that. But if no matter what, so because it's a constant, that's really 0. So I could have plugged that 50 in the beginning. That's not a big deal. But so this side's going to be equal to 0 because 2 times 50 times 0, you get the point. Now let's plug in what I know. I know that we'll say this is A here and this is B here. Okay, so A is 30, so 2 times 30. It's pulling away at 3 feet per second. That's my dAdt, so that's going to be 3. Plus 2 times, what's B? Well, if I do the math for 30, 50, this is going to be a 40-foot value, height of the wall. Okay, so we know B is 40, and we do not know dB over dt. And that's what we're trying to find. Once I do the math, this is 60 times 3 is 180. Let's subtract it. And then divide by 80, right? So it's negative 180 over 80. That is equal to dB over dt. And then I get negative, I don't know, 2.25. 2.25 feet per second because it's falling at a rate of 2.25 feet per second. All right. What else do I need to do? Oh yeah, I gotta find acceleration. I got to find acceleration. How do I find acceleration? Well, remember, acceleration is the double derivative. So I found the first derivative. Now I need to find the second. Okay? So I need to find the second derivative of this implicit value. So let me erase some stuff. Maybe I'll do it over here. Maybe I'll do it on this side. So again, I have your 2a dA dt plus 2b dB dt equals 2c dc dt. Okay? Great. Well, what else do I know? I'm going to divide everything by 2 because everything's got a 2 there, so I can do that. I get a, dA dt plus b dB dt equals c dc dt. Cool. I know to find the double derivative of this. Okay, so how do I do that? Well, these are all product rules. That's a product rule, that's a product rule, that's a product rule. So now let's do it. How do I do it? Let's find out. Oops, this is dc over dt. So if I find the derivative of this is product rule, so it's u and then v. So u is a and v is dA dt. I'm going to find the derivative of dA dt. Well, guess what that is? That's just d squared a over dt squared times a plus, what's the derivative of a? Well, a is just dA over dt times dA over dt. So that's just squared, right? Fantastic. Hopefully we see that. plus, now the same thing is going to apply for all of these, plus b d squared b over dt squared, plus, now I'm taking the derivative of b, which is db dt, times the db dt that's there, so I get db dt squared equals, and then I'm going to do this, I get c d squared c over dt squared plus dc over dt squared. Alright, let me erase some of the other garbage. Let's do that. Alright. Okay, so now what happens? Now I can plug in what I know. I know that the a value is 30. Okay? I do not know what d squared a is over dt squared. I don't know what that is, so I can't do any of these values here. Oh, I'm kidding. I do know. I don't know what I'm thinking about. I don't know what d squared a over dt squared is, but I do know what dA over dt is, and because that's that squared, okay, let me back up here. I get d squared a over dt squared plus, well, dA over dt, well, that was just 3. Because remember, oh, that was a terrible vertical line. This was my thing. This was moving in this direction at 3 feet per second. This was 30. This was 50. I'm going down, but that's really 40, okay, after the math. And so dA is 3, so 3 squared, plus the b value, which is 40, because that's the other value there, a, b, c, right, for Pythagorean theorem. 40 times d squared b over dt squared, we don't know what that value is, plus, we do know what db over dt was, that was negative 9/4. Oh yeah, I was supposed to reduce the negative 180 over 80, sorry, that's negative 9/4, it's negative 90 over 40, and then cut those, and then negative 9/4, right? And so that's negative 9/4 squared, that's cool. Then we know that c, the value, is the hypotenuse, that's 50. We don't know what d squared c is over dt squared. And then I do know, oops, that because the it's a constant, and I'm evaluating a constant, square it, right? So that's just 0 squared. All right, this is cool. This is cool. So now what happens? Well, let me. Can I scroll? Oh, I can scroll down a little bit. Okay, cool. Cool. Now let's think about what this really means. Because it's the double derivative, okay, and I already used 30, 40, and 50. All right, those were the 30 was given to us, right? The 50 was originally, right? So the 50 was original. Where is it at? Up here somewhere, right? Actually, right there. Okay, the 50 was original. The 30 is what I used to find the 40 value of the Pythagorean theorem. So the 30 was important for the first derivative in order to find it. That's what I needed to find afterwards. But now in this double derivative, it's now a constant. And so because 30 is now a constant, d squared a over dt squared goes to 0 as well. So this is 30 times 0 plus, this is 9, plus, we also do not know what d squared b is over dt squared. The reason we do not know this is we used the 30 and the 50 for the first derivative. So the 40 came from after we did the derivative, after we found the Pythagorean theorem. That 40 was used then. So in this case, we're trying to find what d squared b is over dt squared. So I cannot just say that's equal to 0. If I were to go one more derivative, in the third derivative, then sure. What is acceleration? What is the next one? I don't know, it's a physics thing or something like that, right? I don't know. That's physics, who cares? So I would go to the next one, but then the next one it would be 0. But in this case, because it's the second derivative, I can't say that goes to 0. So it's 40 times d squared b over dt squared plus, this is just 81 over 16 equals the d squared c over dt squared. Well, if dc over dt was 0, then dc squared over dt squared is going to be 0. So 50 times 0 plus 0 squared. Okay? Great, 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 great. So now do the math, okay? 30 times 0 obviously is 0. So 9 plus 81 over 16. And I'm going to, this is all 0 over here. And so my answer is going to be basically like d squared b over dt squared is equal to negative 9 minus 81 over 16. And all of that's basically over 40. Okay? And this is going to be equal to around negative 0.352 feet per second, or feet per second squared. Okay? That's a hard one. That's a very tough one. So you got to think about kind of what it's asking. Jerk. That's the third one. So it's position, velocity, acceleration, jerk. That's it. That's physics. Okay? And anyway, that doesn't matter for this, but I'm just telling you. That's what it would be. All right? This is the acceleration of the ladder when it's coming down the base of the hill, or the base of the hill, the building, right? So it's getting pulled, so it's coming down at a rate of negative 0.352 feet per second, right? That's the acceleration at that value. Okay, that's it for this video. It's going to be a fun one, especially the next one. All right, deuces, my gooses.